In this video, we're diving into the world of time complexity notations, which are essential for understanding the efficiency of algorithms. We'll explore the three primary notations used in asymptotic analysis: Big O, omega, and theta. Each of these notations provides a different way to describe how an algorithm's runtime grows as the input size increases. Understanding these notations will give you a solid foundation for evaluating and comparing the performance of different algorithms. Asymptotic analysis is a technique used to describe the limiting behavior of a function. In the context of algorithms, it means we focus on how the runtime or space requirements grow as the input size gets very large. First, it focuses on the behavior as input size grows, rather than concerning ourselves with the performance on small inputs. Second, it analyzes algorithm efficiency. Third, asymptotic analysis ignores constant factors. Finally, it provides mathematical framework for algorithm comparison. Big O notation, denoted as O of f of n, is an upper bound representation that describes the worst-case scenario of an algorithm's time complexity. It represents the upper limit of the growth rate, telling us the maximum amount of time an algorithm might take. It focuses on worst-case performance, providing a guarantee that the algorithm will not be slower than this bound. It is the most commonly used notation in algorithm analysis. Mathematically, f of n is less than or equal to c times g of n for large n. Consider the example of a linear search algorithm in Python. In the worst-case scenario, the target element is not in the array, and the algorithm has to iterate through all n elements, resulting in a time complexity of O of n. Here are some common Big O complexities that you'll encounter frequently. O of 1 represents constant time, where the operations don't depend on the input size. Examples include array indexing and hash table lookup. O of log n represents logarithmic time, where operations divide the problem in half each time. Examples include binary search and balance trees. O of n represents linear time, where operations process each element once. Examples include linear search and traversing arrays. O of n log n represents linearithmic time, which is often seen in efficient sorting algorithms like merge sort, heap sort, and quick sort. O of n squared represents quadratic time, where operations have nested loops over the data, such as bubble sort and insertion sort. Finally, O of 2 to the power of n represents exponential time, where operations double with each addition to the input, as seen in recursive Fibonacci and towers of Hanoi. Omega notation, denoted as omega of f of n, is a lower bound representation that describes the best-case scenario of an algorithm's time complexity. It represents the lower limit of growth rate, indicating the minimum amount of time an algorithm could take. It focuses on best-case performance, showing the fastest possible execution. Mathematically, f of n is greater than or equal to c times g of n for large n. Omega is less commonly used than Big O in practice. The shaded region below the curve represents the lower bound. The algorithm's actual performance will always be above this line. Theta notation, denoted as theta of f of n, is a tight-bound representation that describes both the upper and lower bounds of an algorithm's time complexity. It represents both upper and lower limits, indicating the exact asymptotic behavior. Mathematically, c1 times g of n is less than or equal to f of n, which is less than or equal to c2 times g of n. Theta is used when an algorithm's best and worst cases are of the same order. Consider an example of array traversal. The calculate_sum function always visits all n elements exactly once, making its time complexity theta of n. Let's compare the notations side by side. Big O notation represents the upper bound, indicating the worst-case scenario. Omega notation represents the lower bound, indicating the best-case scenario. Theta notation represents the tight bound, indicating the average-case scenario. When theta of n exists, both O of n and omega of n must be true. In the table we have three columns. First column is notation, second is description, and the third is the use case. Big O notation describes upper bound, and it is most common in algorithm analysis. Omega notation describes lower bound, and it is used in proving algorithm efficiency lower limits. Theta notation describes tight bound, and it is used when upper and lower bounds match. Let's look at some real-world algorithm examples. First, we have binary search. It has a big O of log n, omega of 1, and theta of log n. It efficiently finds an element in a sorted array by repeatedly dividing the search space in half. The best case occurs when the target is in the middle. Second, we have quicksort. It has a big O of n squared, omega of n log n, and theta of n log n. It is a divide-and-conquer sorting algorithm that picks a pivot and partitions the array. The average case is n log n, but the worst case occurs with bad pivot selection. Third, we have hash table lookup. It has a big O of n omega of 1 and theta of 1. It provides direct access to elements by key. O of 1 in the average case, but can degrade to O of n in the worst case with hash collisions and poor hash functions. Finally, we have breadth-first search. It has a big O of v plus e, omega of v plus e, and theta of v plus e. It's a graph traversal that visits all vertices at the current depth before moving deeper. Complexity depends on vertices v and edges e. Here's a step-by-step guide on how to analyze algorithm time complexity. Step 1. Identify basic operations such as comparisons and assignments. Step 2. Count operations as a function of the input size, n. Step 3. Identify dominant terms which are the highest power of n. Step 4. Drop constants and lower-order terms. Step 5. Express the final complexity using appropriate notation. Let's consider a function with nested loops. The outer loop has a time complexity of O of n, and the inner loop also has a time complexity of O of n. Therefore, the total complexity is O of n times O of n, which equals O of n squared. Let's summarize the key takeaways from this video. First, time complexity is crucial for understanding algorithm efficiency and scalability. Second, big O, omega, and theta notations provide different perspectives on algorithm performance. Third, big O is most commonly used for practical algorithm analysis. Fourth, focus on the dominant terms and ignore constants for asymptotic analysis. Finally, efficient algorithms can make the difference between viable and impractical solutions. Big O represents the upper bound, omega represents the lower bound, and theta represents the tight bound. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.